Warner. Welcome back to this episode of the Ecosystem Podcast. Today, I have the Power Trio for you as we go into DesignCon 2026 next week. Today, I'm talking to Steve Sandler of Picotest, Heidi Barnes of Keysight, and Ben Dannan of Signal Edge Solution. These really are the trifecta of the power delivery and power integrity technology space. Together, they're presenting 17 papers combined, including 2 papers and 1 tutorial that they'll be presenting at DesignCon. They're going to talk about how things are shifting in this era of AI data center and high performance compute, and they are at the leading or bleeding edge of technology, and you're going to learn a lot from this episode. I've also packed the show notes with lots of helpful links to both their website if you're not attending DesignCon and their session links if you are able to attend. Without further ado, let's jump into our conversation with Steve, Heidi, and Ben. Hello, Steve, Ben, and Heidi. So good to see you again for our annual DesignCon connection here. You guys have more work than ever on your plates. It seems like you're scattered all over the DesignCon 2026 calendar. And I'm curious to know both why that is. And Steve, why don't you tee off and tell us a little bit about the tutorial that the three of you are doing together?
Sure. Let me start by saying that the goal was to do less this year. That was a goal that we set last year after realizing how busy, we all are. But I don't know, Heidi, Ben, and I, we just have this in us. But I think it wasn't really by choice that we ended up so busy. This is the result of AI data center HPC putting tremendous pressure on engineers to deliver. And, they say stuff rolls downhill. And so they're under pressure to deliver and running into all kinds of obstacles. And so that flows down to us to deliver what are these new solutions? What are the problems that are in the way? And how do we resolve those? And I think that, when we got together to do these papers this year, it didn't really just kind of come together as bam. It kind of, and then there's one more, and then there's one more. But one thing I think that we all wanted to really try to pay attention to this year is we really wanted to do work that was going to influence engineers now. We wanted something that was going to be immediately helpful material that they could take back to their jobs and face their challenges better than they could before DesignCon. And I think that was the goal that all three of us had.
So tell us a bit about your I think it's Tuesday that the three of you are doing a tutorial. So why don't you tell us about overall what the title of that and what people can expect to learn in your part, and then we'll just go around to Heidi and Ben and talk about your different parts of that presentation.
Sure. So, calibration, the tutorial is actually called Calibrate Right or Measure Wrong. And calibration has always been on my radar. It's something that, we addressed a couple of years ago, but I don't think deeply enough. And again, I'm going to push this back to AI data center. Because of AI data center, there's new components. People are trying to push, ESL, component inductance, parasitic inductance down to improve distribution networks. And it got to the point that it became really challenging to try to even measure these components, much less accurately. And so what we did was we came up with a Picotest. We derived some new fixtures that would allow us to measure these tiny parasitics, and then developed methodologies for how it is that we would calibrate them for instruments that people were actually using today. And this became a many part thing because, being able to make the measurement, that's one piece. And there's not a measurement, there's hundreds of measurements. And so, I'm going to pass it off to Ben for that because Ben and his folks at Signal Edge Solutions, they did many of the measurements. But then beyond that, it comes down to how do we do the de-embedding and how do we create the models? In the old days, we used to say you short them out and subtract it. Well, it turns out that's not good enough anymore either. And so that put pressure on Heidi in the simulation world to figure out how do we accurately de-embed this properly. And so that's kind of how it came about. We felt like it needed to be in a tutorial setting because there's so much, not only that there's so much information, but as Ben will tell you, it's very mind bending. And when you first start out trying to get through this, your head wants to explode. And it really takes a while for it to sink in, settle out, and finally go, oh, now I get it. And so in a paper environment, that just wouldn't work. But I'm going to hand it off to Ben because he did most of the heavy lifting at SES.
Yeah, so this was quite a fun journey with Steve, right? So this tutorial we brought in a couple other colleagues from SES, Emily Tan and Tyler Huddleston, and so we learned a lot working with Steve and Heidi on this whole process. Big picture, right? I mean, like Steve said, we're measuring down in the picohenry range and in the double-digit picohenry range with very little error, and so that was the challenge, right? That Steve had to come up with, and we had to kind of help Steve test and make sure it's repeatable, reliable. How do you do that? And the other question is like, all right, well, how do I build something I know to even measure to start this process? And this is, as Steve said, being driven by companies like Saris, Micro Devices, Empower, and other companies that are making these crazy components where they say the ESLs are down in like 10, 20 picohenry range. And we're actually measuring these components and seeing that they're in those sort of magnitudes. And so what people are screaming for, because the industry really has no aligned standard on what to use for simulation in the EM environment, like when you're doing stuff in ADS, is what's the model I need to use, or when do I use this model? What's that model? What's the process? How do I de-embed it? How do I pull that into ADS and make sure that I'm not I have the right inductance? There's all these rules of thumb out there. And so what we're trying to do is basically not debunk that, but kind of clear the air, right? To ultimately help people move forward in the right direction in a more efficient manner, right? Provide key takeaways and a key process that helps you, whether you're using a Bodhi 100, 500, or an ENA from Keysight, right? Like an E5061 Bravo. So there's lots of challenges out there. And again, as Steve basically kicked off, it's really driven by the AI and data center environment. And if you look at any high current solution today, whether you're designing with like a high current FPGA, like a Versal, these problems are all creeping up to the same levels too.
So, Heidi, it sounds like ADS is right in the center of all of this. And as Steve often says, Keysight ADS is one of the few end-to-end solutions. So, why don't you tell us about your piece of that tutorial, and how that fits in to the mix of what Steve and Ben are doing?
Right. No, I think, the this tutorial, we keep thinking, the two-port shunt, it's been around for a while. We've explained it, every year, maybe for for 10, 15, 20 years, and we keep thinking we're done. And then we realize it's not a simple thing. And there's a famous quote, or not a famous, the quote I liked that I picked up from DesignCon, and I'm forgetting who said it, but you know, everybody believes the simulation. I mean, I would say everybody believes the measurement. Okay,
Right.
because it's hardware, it's real. You take a measurement, that's got to be right. And then, except for the problem is the person taking that measurement, when they go and take that measurement one day and they come back and they do it the next day, it's not always the same. So the repeatability is a challenge a lot of times, and that has to do with calibration. And then the other side of the coin is nobody believes simulation except for the person doing the simulation. Because if I set up a simulation and I hit the button, I get the same answer every time on that simulation. So they're two very different worlds, but the simulation's only valid if you can use correct models, and so you need that from measurement. And then measurement, if you do right calibrations and things like that, you can get the right models, but you can't always measure what you want to. And so that's where simulation comes in, because simulation can then extrapolate and how do I say, look at places or look at things that the measurement really can't do efficiently. So it's the two together that really provide our ability to push this AI cloud compute and do these, really predict and design the electronics of the future. So you're really, really seeing this combination of simulation and measurement starting to work together. But back to our tutorial on calibration and this methodology here, it's kind of interesting. We're trying to measure microohms, the very, very tiny impedances, and yet we're using a 50 ohm network analyzer. So the way we're using it is not traditional. And then that means the way we calibrate is not necessarily traditional. And so that's the importance of this tutorial. It's not hard. Once you figure it out and you look back, it looks easy. But when you're new to it, it's rather complicated. And this tutorial is very important to explain those differences. And then I think the one little piece of the puzzle that I'm bringing to this tutorial that I'm excited about is I'm actually a co-chair on the IEEE, Electronic Packaging Society, Electronic Design Modeling and Simulation Society. And I've done a lot of work with this committee on benchmarking. And we have a benchmark that we're doing with Istvan Novak on how to measure a single via. And everyone says, well, that's silly. It's microohms and 20 picohenries or picohenries of inductance. Why are we measuring something that small? Well, the problem is if you take a cloud compute FPGA giant processor with thousands of these very tiny vias, the inductance doesn't get bigger, it gets smaller. And so the parallelization of all these vias is really what we're after, is understanding how low can we get this impedance when we're delivering power from our regulators to our load. And so if we can't measure one via, how do we think we're going to measure 1,000 via PDN? So that's the challenge. And we're there's methodologies and calibrations, and I think it's very exciting to show how well we can do this with pushing the measurement technology and understanding it through simulation.
Well, from a high level, of course, power is at the forefront of all things AI and data center. You can hear that on the news. And knowing that this is becoming more critical, not less, puts you guys sort of right in the center. So it sort of makes sense to me. And also this whole idea of shift left, of being able to simulate that ahead of building very expensive hardware seems like something, and getting the calibration right seems like something engineers are going to have to do.
Yeah,
Um,
one of the challenges and one of the reasons this floated to the top is that we do tend to want to correlate our measurements and our simulations, and they're supposed to match. And so just, a year ago, if we were measuring 500 picohenries and we could get within 50, that's pretty good, right? 10%, the error doesn't look very big. Now you measure components at 20 picohenries and 50 picohenries is a 300% error. Um, and so things have really changed an awful lot. And so that's driving people to try to make these measurements like Istvan. And as I said earlier, stuff flows downhill. So Istvan needs to go measure a picohenry. And how do you measure a picohenry? Well, you need crazy isolators and source power amplifiers. So I get a knock on the door from Istvan saying, hey, can you make me this isolator and can you make me that source power amplifier so I can measure a picohenry? And it just keeps going and going and going. And next year, I'm sure we're going to be talking about single digit picohenry components because it doesn't stop. Our job is just to keep up.
Mhm.
yeah. What were you going to say, Heidi?
Oh, no, just that it's been exciting to see how all of coming from different directions from both the measurement and the simulation. And I think one final thing that I always say about that kind of eye-opening to me was, you think about picohenries, 10 picohenries, 20 picohenries. That's a really small inductance and a lot of people, it's a parasitic that we're worrying about essentially, of the printed circuit board, of the mounting inductance of these capacitors and different components. But what was eye-opening to me is even a resistor, has inductance. But if you look at where 10 picohenries where if you're down at microohms, say 10 microohms, if you're following that 10 microohms impedance across and you hit a 10 picohenry inductor, you're in, the hundreds of kilohertz where it starts becoming reactive, where it starts becoming an inductor. And it's not in the gigahertz. Most of people think 10 picohenries, oh, that's my RF microwave. That's where you worry about that. But down in the hundreds of kilohertz, when you have these AI cloud compute power delivery networks that are down into the, low digit microohms, you have to start worrying about these, the RF microwave behavior starts impacting you in the hundreds of kilohertz. So it's not DC, it's AC, and it's RF microwave transmission line effects that are impacting this AI cloud compute power delivery down into the hundreds of kilohertz, not up at the, gigahertz region.
Yeah, and to your point, Heidi, I mean, all the stuff that we learned that we're teaching this tutorial, we applied to 2 of our papers, right? With what we're showing, because Judy, we have 2 papers, Steve, Heidi, and I, that we collaborated on, right? One is where we worked with Qnity, right? And I'll let Heidi talk to that one, but we basically built hardware with a 2000 amp Picotest custom load fixture, and we're showing with and without embedded caps what the impact is. And then another one where we show on a multi-quadrant step load fixture from Picotest, or how to model and measure ground balance and crosstalk. And there was a ton of learning of both those. And in the last one with the crosstalk and ground balance paper, we iterated the hardware 3 times within the timeline for the paper development just to get it all right. And there was a ton of collaboration amongst an awesome team, right? We have colleagues from Northrop and Broadcom also collaborating on this paper, Will McCaffrey and Adam Ben Ezra. And so we are showing in this paper with the methods that we learned from this tutorial that we're going to teach, right, how to get single digit correlation in terms of millivolts, in terms of crosstalk and ground balance. But that started with building good fundamental models, right? And that's where it started. And we rolled that into this. And ultimately, right, using some of these new fixtures from Picotest, right, and the methods we're teaching on how to calibrate, like Heidi and Steve talked about, this is what people really want to know, right? And how to make it easier.
Well, I love that you're bringing the 3 of you together, plus the whole team in the background. It's phenomenal. And just for our listeners, real quick, everything we're going to talk about today, I'm going to put in the show notes. So if you are attending DesignCon, then you can go right to those pages and add them to your schedule. Let's quickly go around. You mentioned 2 papers that you're doing together. Steve, dare I ask how many papers and presentations you're doing? And then I'll ask the same of Ben and Heidi.
I promised I was going to slow down this year, but I did end up with 7 sessions at DesignCon, which includes a power hour, power integrity discussion at the Tektronix booth, and also a video on the new time domain Sepia solution. But to Ben's point, these new boards that we made for crosstalk and embedded capacitor evaluation, we also learned that the way that we were measuring the voltage transients and power integrity didn't actually work. In fact, you might have a voltage window of 30 millivolts. And in my first attempt, I realized that I had 30 millivolts of uncertainty. And so how do you measure 30 millivolts with 30 millivolts of uncertainty? And what does that even mean? Tektronix saw that, and they really doubted it. They should have known better, but they doubted it. And so they tried to repeat the same experiment, also using one of our 2000 amp boards, and they got the same answer, which shocked them. And that is actually a paper that I'm a co-author on, but the heavy lifting was done by Seamus Brokaw, a young engineer at Tektronix. And Ben said, well, I mean, this is mind distorting, right? This kind of destroys everything we know about just using a probe. How can this be? And so Ben repeated it on his Rode instrument and got the same answer too. And we turned around and said, so we were all measuring 30 millivolts with 30 millivolts of uncertainty. And so it began with not measuring these boards. It began with learning to measure these boards. And so that became a paper. And then Sepia became popular. I wrote Sepia back in 2011-ish, and there wasn't any interest in it. And all of a sudden, now everybody's interested. And they're interested because the measurements at 2000 amps have become so difficult, and vector network analyzers can't create big enough signals. And that's why we make these 2000 amp step loaders. But then we get this picture, and if we measure it right, we end up with a picture in time domain. What do we do with that? Nobody knows what to do with that. Well, that's what SEPIA was designed for. And so now everybody's looking to SEPIA to see how can we use that to solve the next level of problems. And I'm gonna let Ben talk about that because Ben did really great stuff with his Pulse Pro, software, and Heidi did a great job getting in this into ADS. But what I'll say is that all of these papers are really, focused on trying to remove barriers to measurements, not only for where AI data center and HPC are now, but where they're going to be over the course of the next couple of years. And in my paper, I did an IEEE paper in Italy last year on time domain assessment. And I said, so I got to where I can give you a picture of the result. I'm not close to telling you what it means or what to do with the result. And so that's, I think, where we're going next is to figure out how we take these new measurements that we've figured out how to do and accurately, and how do we create entirely new assessments based on them.
Ben, why don't you talk about the sepia?
Sure. Yeah. So there's a session that I'm doing with Rody as one of the 5 topics that I'm presenting on at DesignCon this year. Then there's a panel, but on the Rody session, right, it's called Beyond the LTI Barrier, Quantitative VRM Stability and PN Optimization from a time domain step load measurement. And it's really based around all on the Sandler sepia algorithm. What we've done is we've taken Steve's sepia math, right, and we wrap software around it and then completely automated the solution. So you can take, say, a scope like an MXO from Rody, a power supply, and with like a simple step load like an S10 from Picotest, and a probe, we can completely automate any stability and measurement for any power supply. And we do all this in under 30 seconds. And we tell you if it's unstable or not. And then we give you a full extracted spice model, all using the math that Sepia gives us, right? It's extremely powerful. And so because we're using browser-based probes, right, we can now move those probes and do a whole board and really under a fraction of the time and completely automate. But the difference with what was done previously is that designers would typically take a power supply, they'd hit it with a step load, look at it, adjust the response, try to get their response to optimally be the correct damping, right? Because if it's unstable, you're going to see a lot of ringing. What we've done with Sepia is that we've completely automated that with StepLoad Pro, where StepLoad Pro, you just tell it go, and it sets basically the step load excitation waveform. It drives that, it auto scales a waveform, sets the trigger, and then does all the post processing for you. And it does it 30 seconds. So
that's objective. It's a quantitative objective measurement. But the latest thing that Ben added is the ability to tell you what the right capacitors were. So now it tells you, it's unstable, but if you put in this capacitor, it'll be fixed.
That's amazing.
Of course, the next step to that'll be synthesizing what it is that the improvement would look like. And if you go all the way back to 2012, when I pitched it, that's exactly what I said it would be. It would live in a scope, it would do the assessment, it would tell you what the right components were, and it would synthesize the corrected solution. And then you could go fix it, measure it, and hopefully it would align. So kind of great to see.
Yeah, and so we worked with Heidi, right? We put Sepia in ADS, and so we'll basically be publishing that next week on our website so people can pull it down for free and then run the Sepia math in ADS also. So now you have this ubiquitous solution to run in both simulation and measurement, kind of like NISM for the folks that are familiar with Steve's NISM algorithm, non-invasive stability measurement, where that's also available for free in ADS and on pretty much every VNA on the market. Right. And so now you have these 2 great solutions, right? One in frequency domain with NISM and one in time domain with Sepia, to allow designers really to choose and use what works for their application from an overall design integration to test and build and model their products.
Yeah, I'm going to let Heidi talk about this, but one of the really cool things that Heidi did is tied all of these together to the state-space average model. And so now this end-to-end simulation in ADS can include NISM, and it can include Sepia and small signal and large signal. in an end-to-end simulation. So they're not even standalone. Heidi's integrated all of those in the ADS environment and ecosystem so that we can use them all in measurement simulation and interactively. It's pretty cool.
Heidi, you want to
Yeah,
take
no, I
this lead there?
this brings up I can't keep up with Steve. I don't have 7 papers and whatnot, but I do have 5 between the tutorial and 3 papers and a panel session. So I will be busy at DesignCon. And Ben is also, he's going to surpass us all eventually, I believe here, but he's got a great company going and very excited. He's got a PDK of these state space average models, VRM models that run in ADS. And so that he's going to be showing that off at his booth at DesignCon. Obviously Picotest is being showing off their spectacular dynamic load, his load stepper. And it's no longer just 2000 amp. He's going, way surpassed that now. But what is really was exciting for me this year, and I see all of this knowledge and all of this capability, the measurement simulation, everything coming together this year, and it's just really exciting to talk about, and I can't wait to see people in our at our papers and talk to them about it. But 2 things. So there's the crosstalk ground bounce paper that I'm working on with Ben and Steve. And that one, obviously we're doing end to end, and that one is a dynamic sync. So we're focusing on that giant step load and how it crosstalks. Does it couple to a victim power rail or signal trace, or is it the actual shared ground that's causing the crosstalk? And so in simulation now, we can easily separate that out. I can put in a reference ground plate. I can do differential excitation, look at differential common mode. I can look at crosstalk, ground bounce, and I can literally see what is the noise on the shared ground versus what's the noise coupling between nets. Very exciting to start having that depth of the simulation to go in and debug the measurements that we're seeing. So really exciting, the correlation that we're seeing there. But I think my most surprising one is actually our embedded capacitance paper, because in order to get a lot of these companies, and we're working with Qnity, which was formerly DuPont, to get embedded capacitance, you can have a high dielectric material, but you can also make a thin dielectric. And by making it a really thin dielectric, you increase the capacitance. Well, what's not intuitive and what we're really going to try to drive home is that this thin dielectric has a much lower in loop inductance to all of the decoupling capacitors. So when you're doing an embedded capacitive material for a 2000 amp design, and that's what we're going to demonstrate, is this 2000 amp step loader with this thin high embedded capacitive material. The thin layer provides more capacitance, but it's so small, it doesn't really impact 2000 amps micro-ohm impedance. What it does do is it lowers the loop inductance, and it's fascinating to see the improvement there. By lowering the loop inductance to all of the decoupling capacitors, they're much more effective. And I was in simulation, I was able to do an end-to-end conducted EMI simulation. So literally from the power connector of 48 volts, dropping down to 12 volts, dropping down to 1 volt with those switching DC to DC converters, going all the way to a 2000 amp dynamic load. The ADS PI Pro simulator allows me to do cascaded VRMs, and I'm bringing that into the ADS schematic, and I have all those models along with the PDN AC impedance models from our EM simulator. I can run that full simulation and actually look at the conducted EMI coming out on the 48 volt connector, and come to the paper and you'll see the results.
Ben, we didn't talk about all the papers you're doing. Why don't you finish us up here and tell us about the various papers that you're presenting at
Sure,
DesignCon?
yes. So 2 papers with Steve and Heidi, the crosstalk paper and ground bounce paper, which we're super excited about. Then we have the embedded cap paper that Heidi already talked about. I already mentioned basically that's that session with Rody where we're talking about when introducing Sepia and automation Then we're doing the tutorial, which we talked about. And last, I'm doing a panel also. So that's the 5th session. My panel is on really advanced packaging technology, right? It's really focused on, some of the challenges from the chiplets and advanced packaging. The part that I'll be talking about primarily is what are the modeling and measurement gaps from an SIPI perspective, right? I mean, Heidi, Steve, and I have been seeing these problems for a while. Heidi's seen real world examples from customers like chiplets with thousands of bumps, right? And these are challenges that we need to model and measure, right? So how do you model that? And then you think about this on the other side when you're in the real world, how do you probe? Where do you probe? And how do we validate these designs, right? When we actually build it. So these are the pieces that I'll be talking about at the panel. So super excited for DesignCon. We have tons of things to show, tons of things to talk about. Come to our booths, right? At Picotest, Keysight, and Singular Solutions. We have a ton of fun stuff. I mean, there's things we didn't even talk about that we built from a demo perspective. Steve's working on these crazy high bandwidth current shunts, 200 megahertz, and he has some gigahertz solutions coming out. So I built a demo using the eval board from Picotest, showing how to measure that with an isolated probe. This is what people want. Like, how do you measure current that with high bandwidth, right? Well, Steve had to figure out how to build that shock, right? And so he's working on that problem with some other partners. And so there's so much going on. People are going to just be overwhelmed, and we're going to have tons of fun. Yeah.
I am overwhelmed, but I'm also excited, as I'm sure all 3 of you are. I'm going to ask a super loaded question as I'm trying to wrap up our time together, because it's been something I've been observing. And you talked about the lines between time domain and frequency domain getting blurred. We were talking, the RF and high speed. These lines are all blurring as the speed curve goes up. So when we're looking at we're looking at boards, chips, and packaging, sort of the whole, and connectors, the whole system. What do you see over the next year? I'm just seeing so much about packaging right now. In fact, I may be attending IMAPS early March, right after DesignCon. Where do you see packaging in this stack, and what engineers may need to be looking at in regards to packaging specifically? And you mentioned, Heidi, which I didn't know, that you've been part of IEEE. Ben, did you say did that? So one of you
That's
also
Heidi.
said.
Heidi is a co-chair on EPEPS, IEEE EPEPS, right?
Yeah, go ahead, Heidi.
Now, Heidi, go ahead.
Right. So I'm on this electronic design modeling and simulation group of the Electronic Packaging Society, and and we do that group. We do help support inputs to the heterogeneous integration roadmap, which is and I think just from a high level looking at things. And I'm actually on a paper with H3C on vertical power delivery. There's a big discussion, lateral versus vertical, and of vertical solutions. I think what we're going to see there, if they're going to work at all, there has to be this very creative, three-dimensional approach to things. And I think, printed circuit boards are planar, and our heads can wrap around that pretty quick. You can get a pretty good grasp on all these this planar structure. You start going to three-dimensional, and the technologies that are available, it's this huge design space, and there's so much creativity. And it's three-dimensional, though. So now it gets very complex, not just in the electrical world of how the electrical fields are all interacting and everything, but you also have mechanical disparity of all these different materials. You have thermal. So it's becoming a very complex multi-physics challenge. And I think you're seeing a lot of AI being thrown at it. You're seeing a lot of creative approaches with EM simulators. This is part of our benchmarking activities, trying to figure out how can we get real world benchmarks so that the modeling and simulation world, our vendors of EM tools, can actually start advancing their tools on real world problems and comparing nodes and really pushing that technology forward. So I think we're not going backwards. It's not going to get easier. It's not going to get less complex. And I think the AI cloud compute stuff, the large language models, That's, I think, going to be really fascinating to see how that's applied. And come to, I am on an AI panel for power integrity that Idan Ben Ezra of Broadcom has pulled together, and Madhavan Swaminathan is on there talking about AI cloud compute for power delivery. And so, yeah, that we're going to have a really good discussion there on this sort of topic.
Yeah, no, Heidi's right. It's not going to go backwards. It's not going to stop anytime soon. But we do know where it's going because of the questions that were being asked now. Why does our high-speed step load have to be so fast? Why are we looking at crosstalk? It's because we're stuffing more into the package, higher integration levels in higher speed devices that are even higher current. And so if you ask these chip designers what scares them, what keeps them up at night, it's fear of crosstalk in a package for a device that they won't have for a few years yet. And so how are they supposed to be designing without that knowledge? So we know that that's a big piece of what's coming. And we also know that's why we're under so much pressure, is to provide that vision. We also know that we have this other problem, and we can talk about vertical power and everything else. Um, but the ultimate bottom line is that, when I mentioned 2000 amps, people say, wow, that's so 2024, right? Because now we're 5, 6, 7, 10. But we don't actually have VRM solutions in that space. We have, very limited options. Much to, I'm sure, Alex Lido's dismay, we haven't embraced or haven't figured out gallium nitride on the low voltage side, which would help us to shrink the power system and get more efficiency. And I'm going to leave you with just this little tease, and that is that I'm not ready to talk about it yet, but I will be ready at APEC.
Okay. Well, I know a little bit about that. One last thing before we go. Again, for our audience, welcome to my world, drinking from the fire hose. I promise I will put everything below for you, including the sepia stuff that Ben and Heidi talked about. But before I let you go, Steve, why don't you tell us about, you've got a book that you collaborated with Ken Kaufman and I think Tektronix on. Why don't you tell the folks a little bit about that before I let you go?
Yeah, so Ken Kaufman is my good friend, and he's also a publisher. And so, one of the things that he thought was that the AI evolution really is pushing our measurement capabilities, and it's forcing us to come up with these new things. But I haven't published a book on measurement since Power Integrity in 2014. And so much has changed, in just those, few years, right? I mean, it's 10 years, but so much in measurement has changed. And so um, the pressure was on to update that book or to write a new book that would adopt all of these new methodologies. And since so much of it is contained within his instruments that Ben showed, just with what he did at Rhodey, so much is embedded in the instruments. And so Ken wanted to put out a book on how we're going to address all of these new measurements and how we would address them in the instrument. Since I'm so involved with Tektronix, that was kind of an obvious connection. But the solutions will apply to other manufacturers also. Like when we talk about isolated probes, Rhodey also has isolated probes. In fact, I'm going to do a session for Rhodey at DesignCon on isolated probes. So it'll carry across brands, but this one focuses on Tektronix instruments because Tektronix is working on their own embedded software. We are going to give away 100 copies of a teaser for that new book, and I do hope that that book will be out in time for DesignCon 2027.
Great. Is there anywhere I can send folks to, I don't know, pre-order or get one of those 100 copies, or what would you suggest there, Steve?
I would say the ticket is to go visit the Picotest booth and just say,
Okay.
"Hey, Steve sent me." You could probably try
Okay.
that at Tektronix too, or maybe show up at the Power Hour. There's only going to be 100 copies, so they're gonna go fast. So what I would suggest is that you get there early, but I'm sure that you'll be able to score one either at the Picotest booth or the Tektronix booth.
Maybe I know somebody named Steve Sandler that might sign a copy. that we could give away here at the ecosystem. Just
I'm
saying.
sure that could happen. And for those that are going to be at DesignCon, Ken Kaufman will be there also.
Okay.
And so I'm sure that you can schmooze him also and talk him out of a copy. Somebody did ask me
Okay.
already if I would sign a copy for him, and I said, if you want me to deface your book for you, I'm happy to do it.
Well, this is always one of my favorite podcasts of the year is getting the three of you together and hear about how you're thinking, the innovation you're doing, and how you're bringing all your knowledge and skill sets together to really empower engineers for next gen, which is coming month after month right now with the speed of innovation. So thank you all for joining me today. I will certainly see you next week at DesignCon. And thank you again for all that you do for the industry and for engineers.
Thanks, Judy.
Thanks for having us.
Yeah.
Yeah, thank you for bringing us together, Judy.
My pleasure. For our audience, make sure you go check out those show notes. They're going to be packed. Sorry about that, but I hope that you'll be happy about that. Let us know if you're at DesignCon next week, and we'd love to connect with you. And make sure you go visit the Picotest booth, the Signal Edge Solution booth, and of course, the Keysight booth. Hopefully, I'll see you next week. Until then, remember to always stay connected to the ecosystem.